Hello there, welcome to another problem session. This is a very interesting problem and it shows up quite a bit. It kind of stumps the students when they come across this problem and they don't know how to actually proceed. However, this is quite a really simple problem, especially when you assume that there is no leakage of magnetic flux. So all the magnetic field is just going around this core and there's no leakage. So you may know the B field is going to go in the core just this direction or the opposite depending on the current. So the core is like this. If the core is wide enough, there will be no leakage. You might think that when it comes out here, comes out over here, there'll be some magnetic field might leak out of this area. It might go like that, but we'll say that it's more like this white. All the magnetic fields are going. All the magnetic fields are just forming a closed loop, and all of them that come here come out here. If come in here, they go through this and come out here. So that's what this means, no leakage. Another thing that kind of bothers and gets people a little bit confused is whenever you have a magnetic field in a material, and if the current is changing, you're going to induce some eddy currents here if the current is changing, and those eddy currents will mess things up a little bit. Of course, they're going to heat up this material and energy will be lost. So you can just ignore the eddy currents. If the current is steady, we can just assume the current is steady. It may be changing a little bit. You can just assume that not changing sufficiently, so there is amount of eddy currents very little, and you can ignore that. So with that kind of caveat, the formula is very easy to obtain. Okay, for that, remember that you have a couple of laws. You have del dot B equal to 0 and del cross H equals to J free plus dd dt, and this has to do with the electric field, so we can just ignore this right now. Okay, so just this, and so this one just says that B at this interface, at this before and after, this is air and this is the iron, so B iron in iron equals to a normal part is coming down. It's coming down normally. B in air normal. So the normal component. So if this is the z-axis, if this is like a z-axis, then this will be Bz in iron equals to Bz in air. So that's one thing we already know. With this, you can convert this into Ampere's law, so that only the flowing current will be involved. So this if I take a loop, closed loop, and I do H dot dl, I go around the loop, then this should be IF enclosed, how much current is enclosed, right? So if I go H is this this blue thing is gonna go H like that. So if I go in that, so is, and dl is the same direction, so H is in parallel to dl, and so there will be something that will be in the core. So H in iron times length of this in iron. So in iron, so the in thing you can just ignore, and then you're gonna have a H in this air part, in air part, L in air part, and the total current will be however number of loops. Let's this number of loops be n over 2 this place and n over 2 this place, so that the total number of loops, they're all going in the same direction. So this will turn out to be n times I. So we have a we have one equation here and second equation here. So we only want in air, so we want over here. So in here between the two, we'll assume that this field is more or less the same value, and so this W is another thing to assume is W is much less than L throughout this. So this is just is W, and this is the entire L of this of the core, and H in air. So this Hz is, these guys is basically HB in iron, because it's going to be all along this direction. B is going like this, and so B in air. So we can convert this into, so this one second equation also in the B. This will be the B in air over mu of air, using B and H relationship. B is equal to mu of the material times H, and mu of the material you can write is equal to vacuum 1 plus chi m of the material, right? So you can write like that. If for iron this thing is about 200, so iron like, you know, or 1,000, you can just say 1,000 times that. Depends on material. Some materials don't have very much, but iron would have a large chi m. Okay, so now this is going to be B in iron over mu of iron, and so if I want this, and B of iron is air, so this becomes B of air, L of this whole thing over mu. Let's call this just mu, mu of the iron, L of the iron, plus W over mu air is like mu zero equals to Ni. So using 1. So the B air is equal to this whole thing, Li over mu I plus W over mu 0 times Ni. So this is the answer. You can of course simplify this, right? Mu is very big. Usually this will be close to 0 compared to this, and this is the only one that will survive. So in here we can say Li over mu I. So say Li is 5 centimeters, even 10 centimeters, okay? And mu I is 1,000. And say W is half a centimeter, and mu 0 times mu 0. So if you convert this is going to be 10 to the power minus 2 1 over mu 0, and W over mu 0 is going to be 1 over 2 mu 0. So this would mean ignore Li over mu I compared to W over mu 0. So I can write this guy, B in air will be directed in this particular current is going to be directed from down up to down, so in this direction, and the magnitude will be just this guy survive, mu 0 over W N I. Okay, so that will be the answer. Let's do a related problem, and that's over here. Instead of using these magnetizable materials and using electromagnets, so this is electromagnet. What if we had the permanent magnets like this, and you have an iron core and permanent magnet? There's no current, flowing current here. So in this case, it's almost identical to that, except that you will see that the B will, this is here the magnets. There's two magnets here. Let me create a gap here. So you have these two magnets. So if you look at the B field, which is yellow, the B field, if this is south and north, and this is also south and north, so in there the B field will go from south to north inside the magnet, continue in the gap, and continue across. It has to continue across. So you have one interface here, another interface here, third. Every interface is going to have to continue, because Bn, the normal part, the normal component of Bn is continuous. So this will just continues, and B will just go like that. We'll assume that no magnetic flux is escaping, just going around everywhere. Okay, so it's all in this. So it will always form it will not go out like that. It will always form a loop. But what happens to let's see, you have one interface here, one interface here, one interface here, one interface here, and we can erase this. When you look at H, which is the blue thing, so H will be now, if you remember, B is 1 over mu naught. B is H over M. So the M is 0 here, not permanent, but of course it's going to magnetize it. M will become smaller, but not 0. It's going to be small compared to over here. So over here, B and M will be same direction, so it will go in that direction. So this is H. But when it comes out here, over here, actually, this is I think this is the south pole and this is the north pole. So the M is this way. But if you put M on the other side, high amount of M on the other side, then you can see the H will become negative. So H will be Instead of this way, H will be that way, and so H will be that way. Now B and H will have to be parallel in this place. So B is in here, B is this way, and in this gap M is 0. So if M is 0, then these guys are parallel, so the H will have to be that way. So you can see the H kind of flips around as it goes through the magnetizable material. Okay. All right, so we want to find out what the B will be here in this case and see if the formulas are very similar. So here, in this case, the known quantities are, like over there, current was given. Known is current, not current, magnetization, and maybe susceptibility of the material. Okay, so such susceptibility of the material. So let's see if we can use this to kind of look similar formula. Formula will be something to do with permeability, this permeability, and the gap and some current. So let's see if we get that. Okay. So I go around in H. So this is a loop in space, and over here H is same direction as the loop. Over here the H, let's H core, HM, and HM is that way, but HA is that way, the air. So in the core, in the air, so that's, if I go around here, it's like that. So if I do H dot dl, so these two HMs, let's see, they're L here and L here, these two added up, well, there's no free current, no free current, this is 0. Okay, so this will be, if I go in the direction HC, I get HC LC, and over here I get minus HM, let's call it this part length be LM over 2, and this part LM over 2, so that together will come, and then HA LA minus HM LM over 2, 0. So we want this, and HM is known, so let's see what do we get. HM LM equals to this guy on the other side, HC LC plus HA LA. So in this medium, this is 1 over mu C BC. In this medium, 1 over mu 0 BA, because it's air. So now this is much bigger than this. So this on the right side, we can say is simply BA mu 0 LA, which is W. So this is simply like that. So HA, I'm assuming this is much other way around, HC LC. So this I'm assuming to make approximation here. So now I'm solving for BA in terms of HM. So BA is mu naught LM over W HM. So HM, what is H? M is known. M is known. So H is chi H is M. and chi m. Mu equals 1 plus chi m mu 0. So you have a mu 0 down here. So chi m is mu minus mu 0 over mu 0. So h is 1 over chi m m. So it flips over mu 0 over mu minus mu 0 m. So that we put in here to get mu 0 Lm over W times mu over mu minus mu 0 times m. And so for this case, B in air is mu naught over W, and then we have this entire thing, which is kind of interesting. Lm and m divided by mu minus mu m Lm over mu minus mu 0. So there it is. So if you look at it, this probably is a number of turns. So this dimension would be dimension of current. Of course, mu has no dimension. Mu or the dimension goes away. So m times Lm. You can see m is dimension of ends is dimension of current times dimension of area, right? Divided by the volume. And so this so the current dimension is m times volume over area is length, and you can see that this whole thing is m times length. So this m and this is length, and the dimension of this cancels the dimension of that. So they are dimensionally check out, and formula is a little bit different, but this is one way you can actually design. Say you wanted to have certain amount of this magnetic field, what kind of magnetization you would need, and what kind of length of the magnet you would need in order for you to actually get that magnetization. So this is very practical. Speaking of practical, I wanted to do some like experimental notations next, okay, that goes with this field of how do you use magnetic field in the lab and what kind of terminology you use, okay. And so that's what this stuff over here is. And so I'm going to spend some 5 minutes or so to explain the meaning of these terms. Okay, so in the lab, a consideration is not necessarily magnetic field, okay, but you want to actually this is a fundamental approximation we are making. Magnetic flux B not leaking out, which normally leaks out. Sometimes even 50% of the magnetic flux leaks out. So you have to be, when you're doing the lab, you have a different kind of notation you use, and you can think of some analogies with electric circuits. Okay, so what's magnetic flux? A magnetic flux will be, if this is B, then n hat dA over some surface. So this defines magnetic flux. This definition. Sometimes we just use, because you can have flux for different fields, you want to put a label to it so that we know whether we're talking about flux of B, flux of H, flux of M, flux of what, any field you can talk about flux. This is just a very general concept. Okay, so let's look at this and this example. So we suppose the poles. So we have another pole was here, and let's area, this radius be A, and this, all the flux has gone through here, and we do this integration over this area. So that's the area over which we integrate. And so if the field is going down, let the normal be the same direction, normal be in the same direction as the field, and assume that the B is uniform on this. So with this B, we are going to get mu naught over W pi A square in I. Okay, so the flux of B in this case, and we assume this flux is this value we obtain around in the air gap is the same over here, same over here, same over here, same over here. So we are assuming that it's the same flux throughout. Okay, so that's what this means. This value is the same. So what we actually, this is the total current that's the flux is built from, right? This flux is built from this total current that in each loop. So number of loops comes with it. So this quantity here, this is what is called magnetomotance. This quantity, the current, the effective current that's responsible for the flux we're looking at. And this quantity over here is actually permeance. So inverse of this, 1 over permeance, is called reluctance. So if you if you look at in electric circuit, you have a I equals to 1 over R times M. This V equals to IR. So we kind of create an analogy between this language and the electric circuit language, where we say voltage is like magnetic motance, which you sometimes EMF. So this is like EMF, electromotive. Sometimes it's called electromotance, in analogy with the same, having similar type of words. And this reluctance is the resistance. So, and you could write this same thing as actually G, letter G is used for so this is conductance. Conductance is equivalent to permeance, and the resistance is related to reluctance. Not related to, is kind of analogous to. So if you look at current comes from integrating J dot n hat dA. So you can say this comes from integrating B dot n dA. So the B is analogous to J. So there is a kind of you can think of magnetic circuits or magnetic field as making makes a circuit, just like a current makes a circuit. And there is a kind of similar language, not the same physics, very different physics, but similar language that one can use. And in the lab, when you're doing a lot of the lab results are actually plotted. So like over here, you would find people plotting V and I, right? So VI diagram, and if it's a resistor, it's just a simple resistor, doesn't depend on voltage or current. So it's going to be V equals IR. You're going to get something like this. And if it's something that actually resistance depends on the voltage, then this will not be linear. So this is the way you study materials, electrical properties of materials. So magnetic properties of materials, what do you plot? You're going to plot, you want to plot flux for this. So magnetic material will be plotting. Let me erase this. So when you're studying magnetic material in the lab, what do you plot? You're going to plot, maybe instead of I, you're going to plot phi B. And on this axis, instead of voltage, you're going to plot magnetomotance. Of course, in this material over here, this is all constant. So here you can just get this. That's going to be this inverse slope. So I'm plotting this on the x and plotting this in the y-axis. And over here, it's just going to be an I. And and the slope will be W over mu naught pi a square. So this is how you do magnetic experiments. Okay, so speaking experiments, next topic I want to talk about is the hysteresis loop that you might have seen, where if you plot B and H, and then you go like this, then we reduce the magnetic field, this H field. You actually don't retrace it, you just go like this and saturate again, and then if you start to increase H, and might get back there. So this is completely magnetization. You remember the H is related to magnetization. Magnetization completely depends on the history, and this thing called hysteresis loop. So in lab, this is very important. So we are going to discuss this next in another video. So see you then. Meanwhile, if you need more, you can go there. That website I maintain. You can subscribe to this channel if you like this kind of deep dives, and hit the like button. Thank you. Bye.